All right, hi everybody. Welcome back to the New York Combinatorics seminar. Today we are very happy to have Parik Chalise here to talk to us from Johns Hopkins University, and he will tell us about a proof of the Gyárfás tree packing conjecture. So thank you very much.
Hi, good afternoon, everybody. Thank you for coming. So today I'm going to talk about proof of Gyárfás tree packing conjecture, as the title says. This is joint work with Antwan Clark and Edinah Gnang. Edinah Gnang is my advisor here at Johns Hopkins, and I would like to especially acknowledge him for doing all he does with me and with others. So let's get into the talk. So I'll be explaining what the conjecture is of Gyárfás. We will convert the problem into something that we do here. We'll convert the problem into a functional language. We'll see what that means. Then we'll convert the problem into a polynomial language. We'll see what that means too. And then I will explain something called composition lemma that yields a proof of the conjecture that we'll see. So first of all, what does it mean to pack graphs? To pack a graph, it means you have, I'll want to write somewhere, if I can figure how. Does anybody know where I click to write with my...
So are you using an iPad?
Yes.
Then you should just be able to write on it, right?
Okay, it's okay. I think it's fine. I didn't see a button. So I have an iPad and a laptop, but it's okay. So let's just define what a graph packing is. So we have a certain collection of graphs, usually smaller graphs, G1 through Gz, and you have a big graph G, and you want to put in these smaller graphs into a big graph G. And if you can put in, then you say you can pack these graphs into the big graph. But if you can pack such that it's perfect, meaning if you can take a union of all these smaller graphs, and the big graph is a union of the smaller graphs, then you perfectly pack smaller graphs into a big graph. So example of this is, let's say I give you these three little graphs, and I want you to pack these little graphs into this bigger graph, G, and I ask you, is it possible? Turns out it is in this case. So you can see this purple one is G1, this orange one is G2, this blue one is G3, and I've formed the graph that I wanted to form. So this is similar to tiling, packing. It's called decomposition somewhere. But general idea is, again, I give you some template graphs that I want you to pack into the larger graph. These may have certain properties, and the bigger graph will have certain template, and you want to put these smaller graphs into the big graph. And again, in this case, you can put them like this. You should observe that the edges are disjoint. My G3 is this blue, G2 is orange, G1 is purple, and I've formed the graph I want to form. And that is all packing means. And this is a perfect packing because I don't have anything left to cover. And I have nothing overlapping. All right, so the Gyárfás tree packing conjecture says any family of tree, T1 through Tn, n different trees, where each tree has k vertices, packs into a complete graph, Kn. You should see that these examples I chose actually are examples of Gyárfás tree pattern for case K4. These are trees on, so trees on one vertex does not have an edge. That's my first graph. This is a tree on two vertices, tree on three vertices, tree on four vertices. And Gyárfás is saying you can take a union of these and put it into a complete graph on four vertices. This earlier one was also three different trees. And for four vertices, these are all possible trees you can have. So for K4, we've proved that Gyárfás's conjecture is true. But then Gyárfás is saying for any n, you take one tree with one edge, one tree with two edge, one tree with three edges, so on and so forth, and the largest tree on n minus one edge. You take a union of them and you should be able to form a complete graph. Notice that this sum, 0 plus 1 plus up to n minus 1, is exactly n choose 2. N choose 2 is the number of edges in a complete graph, and these are number of edges in each of these trees. And because this sum is equal, it means it is possible, arithmetically, it is possible that you can take a tree with one edge, a tree with two edges, and so on and so forth, up to a tree with n minus one edge, and be able to form and choose two edges. This is the minimum requirement. Okay, this is where I wanted to write. So for stars, it is quite easy to see that if you take any sequence of stars, you can pack complete graph. So let's say I take a star on one vertex, which is this. Then I have packed complete graph on one vertex, right? If I now take a star on two vertices, so this conjecture is saying I can make K2, and of course I take that star on one vertex, this star on two vertex, and I've formed K2. If I want to form a K3, I need to take a star on one vertex, star on two vertex, and star on three vertex. Surely I can take a star on three vertex. I already have a star on one vertex and star on two vertex, and I've formed K3. And you can do this to form a K4. I only need to add one more star on K. To form a K4, I just added a star on four vertices, and you can see if I add another star, now on five vertices, I make K5. And so for stars, this is an easy problem. But then stars are not the only trees, right? There is this many trees. This is a sequence of how many trees there are on n. So I've highlighted a number of trees on 23 vertices. There are about 5.6 million trees in 23 vertices. And what Gyárfás conjecture is saying is, if you take any one of these tree, any one of this tree, any one of this tree, so on and so forth, whatever tree I give you, you should be able to make for this a complete graph on 23 vertices. All right. Any questions so far? I hope everybody understands what the problem is. Okay. So there's been a lot of work on this. In 1976, that's the first paper where Gyárfás conjectured this must be true. They proved for if all graphs, but two of them are stars, if everything is either a path or a star, they proved it. Bolovas proved if it's hard to pack the bigger trees, but if you take, this is about 70% of smaller trees, then you can put them into a complete graph. There will be some edges that's not covered in the complete graph, but the smaller trees, it's not too difficult. Turns out bigger trees are difficult, so in 1987, they were able to prove only 3 largest trees, at least you can put into a complete graph. If you skip one largest tree, then you should be able to put this many largest trees. Then in 17, they finally got up to 5 trees. You can put 5 largest trees. In 2021, there was a result that said if the largest degree of the trees are bounded by n over log n, then you should be able. So the problem is either large trees or trees with big degrees. Those are hard to pack. The best result so far, I guess, is they showed there exists a number for any. So if you want to pack k largest trees, then there is an n large enough so that you can pack this large. There's a linear number of trees you can pack into complete graph. So this has given trouble for a long time because of how different trees can be. So until I guess then we worked on it recently, and turns out the methods that we use is able to resolve this for all trees for all n. So how do we do it? The majority of the essence, I guess, of the proof relies on this fact that trees can be represented as functions. Specifically, it can be represented as a function with a fixed point. And I will give an example of what I mean by that now. By the way, Zn is just a set of first n natural numbers. So Zn is from 0 to n minus 1. This is a set. So G is a function from this set of numbers to this set of numbers. And if you compose that function n minus 1 times, the size of the image is 1. That means if you compose enough time, you have you point to a single point. So what does that mean? Let's make any tree. Let's say we have a tree that looks like, say, this. For any tree, you can arbitrarily choose a root and call this a root. After you choose this root, by definition, every other vertex has a unique path to this root. So if you choose this, there is a unique path that comes from every other vertex. So you can orient these edges such that you make these paths to that vertex. And you can put a self loop around that vertex. Then if you give numbers to these vertices arbitrarily, you end up defining a function because, for example, G of 0 is 0. G of 1, this writing is terrible, I'm sorry, is 0. You can see G of 2 is 0, G of 3 is 2, G of 4 is 2, and so on and so forth. So after you choose a root, by definition of tree, everything should have a unique path to the root. And if you put numbers in, it ends up defining a function. Good thing about function is you can compose them. So G of 3 is 2. But then if you compose G of 3 is 2. If you take G again, so G of 3 is G of 2, which is 0. So when you compose, what happens to the tree is the tree changes so that this guy goes there, this guy goes there, this guy still goes there, and this guy goes there, and this guy still goes there. But what you can see is you end up getting your edges closer to the root. And if you compose enough times, any tree, you can choose a root. Yeah, you compose enough time, you see that all trees after enough composition become such that all of them are pointing to the root, right? Yeah, so everything points to the root. Now, this is a star. If you think now, forget the arrows and forget the labels. What you get is a star. So any tree, you can make it into a function. You can compose it and change it to a star. That's the basic backbone of whatever we're going to talk about. Okay, so now we know trees can be functions. When you compose them enough times, you get to a fixed point. But the conjecture requires you not only one tree, it requires you a sequence of tree, right? You want one tree on one vertex, one tree on two vertex, one tree on three vertex, up to a tree on n vertex. But what you can do is now take n of those functions, each in Zn to Zn, and there's n of those, such that this says you control the size. And I have an example to show this, what this means. This is saying, given a sequence of trees, let's say I give you a sequence like this, you can convert it to a functional tree. To be a functional tree means you associate it to a function. So this tree is this function. This tree is this function. I just put numbers and put the arrows, right? But then I augment it by putting these extra loop edges where this guy is only with one vertex, but when I make it functional, I want to make it an n vertex. So all trees are n vertices. And to make it n, I just add extra loop edges. That's all I did. Does the definition of augmented tree sequence make sense? All right, so why do we want augmented tree sequence? Because to be a perfect packing, what you want to do is, remember in a functional graph, there is an edge from V to G of V. This forms an edge. And what we want to do in a perfect packing is to take union of these edges such that the overall union forms all edges of the complete graph. And what these permutations are doing is, maybe the random labeling you chose does not pack the complete graph. We want to relabel these functions. So we may have to put some sigma on each of these edges. And we may have to put sigma such that we relabel each tree separately. But what we want to do is we want to relabel these edges such that when you take a union of all these edges, you end up getting all edges of the complete graph. This is all that's saying. And the point of making them augmented was, if you want to permute them, you want all n vertices to be present so that you can reshuffle your vertex labels however you want. And an example of this is, so I take this sequences of augmented functional trees, and you label them such that when you take a union of them, turns out this is actually a complete graph. So if this guy was labeled such that this was not 0 and 1, but this was 0 and 2, notice it would have collided with this guy, and it would not be a perfect packing. So to be a perfect packing, you want to label them, label the vertices, such that then permute the vertices, such that when you take a union of all your template graphs, you get this complete graph with self-loops. But then we can remove the self-loop at the end because the conjecture originally does not care about self-loops. And self-loop was an artifact of us trying to turn this tree into a function. All this saying is stars. We already saw how stars, a sequence of stars, pack. I drew an example of it earlier, but this is saying if you choose your root to be, if this tree part is on two vertices, if you choose the root to be on the largest label, then if you take a union, you're always going to get a packing for stars. So essentially for stars, it's very easy to pack a sequence of trees. Okay, now we've defined a tree in terms of functions, in terms of contractive functions, so that we can permute these labels of this function and take a union of these edges and form the complete graph. That was an idea that we need to use, but the major tool that we use to prove it is to construct this polynomial. And this polynomial is very similar to this definition here. So this is saying you should be able to take these edges of this graph such that the edges actually give you all edges of the complete graph. What this is saying is exactly the same. This is saying for every k is different trees. You have n different trees. Each of those vertices need to be different, because if it is not different, then it will be 0. And for every edges, the edge levels that you assign to them must be different. So these will make edge levels. I'll say what that is later. But this is saying all the vertex levels are different. And this is saying all the edge levels are distinct. Because if you are not distinct, then this polynomial will become 0. So you want to put numbers in these variables. There are n square variables given to n square vertices in n trees. So when you put them in, you want all the vertices to be different. You want all the edges to be different. Now, how do we make these edge levels? A particular edge level is this. I'll give an example again later, but this is just saying your edges are always going to be from v to g of v, right? And for a particular kth, if you are in the kth tree, then it's going to be this is your of the particular tree. For the particular tree, this is going to be the edge level, because the edge goes from v to g of v for that particular sequence. I think an example of this will make it very clear. Okay. I still need to learn how to. Please feel free to ask questions if you have any question about how we're setting up this problem into a new language so far. All right, if not, maybe I can draw an example. So let's say I want to pack K3, and that's not too difficult, but let's say we don't know how to, and we want to use this polynomial language. We are given 3 trees like this, right? These are the only possible 3 trees you can give me. I want to first convert this into a functional tree, and I can do it however I want. I want to put in numbers. Let's say I want to put 1 and 0, and I put here 0, and I put here I'll put here 2. I'll put here 0, or maybe I want 1. I don't know. I can make this into a functional tree. But then I don't only want the functional tree, I want it to be augmented so that everybody has equal number of vertices. And to be augmented, I just need to add these extra self loops, because they don't hurt. Okay, now I have made my functional sequence of augmented functional trees. Now I want to take a union of those, but the way I want to take union is I want to define edge labels, right? So the edge label is defined by, so for this particular edge, it's going to be y minus 0 times y minus 1. So it just takes, because 0 goes to 1, I will create this label for it. Observe that this guy here will also have the, this is also 0 going to 1, so this will also have the label y minus 0, y minus 1. Remember, in our polynomial, what we are checking is the difference between these labels. So we're checking labels, so that the labels that we assign to these, each of the edges, must be distinct. But the way I put my numbers in, this is saying at some point the polynomial will check this label with this label, and everything is a product, so this will cause a problem because entire polynomial is going to be 0. So there should be another way to assign numbers to these vertices to begin with, so that my edge labels that I induce will be different. So instead, maybe I'll label this guy to be 2 and label this guy to be 1. Then you can already see if you want to form a K3 with these guys, if this is 0 and 1 and 2, this guy will go to 0 goes to 1, this is going 0 to 2, and 1 to 2, and then there is self loops that comes from everywhere. So we've done it. So we should have also done it in the polynomial sense. But you can see we have done it because this label is y minus 0, y minus 1. This label is y minus 0 times y minus 2. And y minus 0 times y minus 2. This guy is y minus 2 times y minus 1. And observe that each of our labels are different. This guy is different from this guy is different from this guy is different from this label, which is y minus 0 times y minus 0. And we do not check, when we check the labels, we don't check for these augmented things. That's how the polynomial is defined. Otherwise, then we would have y minus 2 times y minus 2. You check with this guy and there will be a trouble. But because in tree packing, we don't care about these extra loopages that we have added. We only added those so that they can also get any numbers when you permute. But then when you check the edges themselves, we only check the actual tree edge labels. So hopefully I have convinced that this polynomial actually checks that after you put in numbers to the vertices of your tree, the edge labels are different, the vertex level are different. If you are able to do that, then you get this union to be all possible edges of your complete graph. That's the setup. And so now our job is to put numbers into, so there is n square variables, and we want to put n square numbers into them from 0 through n minus 1, so that this polynomial is not 0. So the conjecture was this: any set of n trees where each tree has k vertex packs into kn. We've converted that each of these trees into a function, actually an augmented function. So each of them not only have k vertex, but everything has n vertex. And because it's a function, we can do that. And we've constructed a polynomial when you put a number for n square variables from Gn. And if you evaluate that polynomial, if it's not 0, then you can actually do this. So this is how we changed the packing problem into a polynomial, problem about polynomial not being 0. So our goal next is to prove there is a point in this lattice. And if you put in that point into the polynomial that we designed, it's not going to be 0. Does everything so far make sense? Please ask questions if you have. Okay. So we need to find a point. When you put the point into a polynomial, it's not 0. Remember the cosine remainder theorem for a single variable? It says something about a point not being 0 for a polynomial. So point t, when you plug it into a polynomial, is not 0 if and only if x minus t is not a factor. Because if this was a factor of the polynomial, then that would mean t is a root of this polynomial, and p of t would be 0. So not 0 means it's not a factor. Observe that this is exactly the same problem that we have. We want a point where the polynomial is not 0. And this theorem is saying something about a point where polynomial is not 0. That same is showing the polynomial mod, the set of roots that you want to forbid, is not 0. And we create a multivariate cosine remainder theorem, exactly in the same spirit. And that says, if there is a point where the polynomial does not vanish, then the polynomial mod this set of, this is all the, because you need to put roots from Zn in each of these things, each of these variables. This is the polynomial that you do not want to be 0. Exactly the same spirit as the single variable. And here I need you guys to trust that this is actually true. This is as the multivariate version of the single variate cosine remainder theorem that says, instead of finding a point where the polynomial that is not 0, we can instead look at this polynomial mod some algebraic relation. And if I can show this is a polynomial, right? We are dividing a polynomial by another polynomial. If I can show this polynomial is not congruent to 0, then that's equivalent to saying there is actually a point where the polynomial does not vanish.
So here you're not working over a field anymore, right? Because you're working in the integers modulo n, or is Zn not the integers mod n, but it's just the set.
Zn is just a set.
Okay, so you still are working over the field of rational numbers. Okay.
Here, this is a polynomial actually. So t is in Zn, but these are n squared different variables. But this is going to fill a fraction, and turns out this will be a polynomial too, and everything works out. This actually follows by induction. You can use single variable to prove the multivariate. Okay, but what we're doing here is this is a degree n polynomial. So if you divide in each variable, if you divide some polynomial by degree n, the remainder needs to have at most degree n minus 1. And when you have degree at most n minus 1, you can write it in Lagrange basis. So this polynomial mod this, it can be represented by this guy, which is the remainder that remains after that, which is, then we can Lagrange interpolate over all the points. But the Lagrange interpolation evaluates this guy at every possible point, and only thing that remain are going to be the one that actually pack. So f is a point in this lattice. If this guy goes to 0, that means the points will not have packed. So this polynomial actually remains if and only if there is a point where PG does not vanish. So all that has happened so far is we are able to write the remainder that you get out of this in a Lagrange basis. And we know exactly what this guy looks like. It's just the definition of Lagrange basis. But then essentially what we have done is now we want to show this guy, this remainder does not vanish identically. It's not a 0 polynomial. So showing a function, not a function, a point exists such that the polynomial doesn't vanish is same as showing the remainder is not identically 0. So we've again overcome the problem of finding a point to showing a polynomial is non-zero. Okay, now this is better showed from example. So I'll just move to example again. So this is saying if you have a sequence of trees, let's say a sequence of trees, I'll again take this same 3 trees. I will compose, let's say this root was here, and this root was here. Everything needs to point to the root, right? There's still your augmented, this extra loop edges that don't really matter. So we have these 3 trees. What happens if you compose them? If you compose them, this guy will become a star, and this guy will also become a star, and this guy will also become a star. I guess this is already a sequence of stars. So if you continue composing each of these guys, it's going to be all stars. So this will be a sequence of stars. So to prove this guy admits a packing, it's enough to prove the iterated guy admits a packing implies the pre-iterated guy admits a packing. If you can show the squares, the sequence of squares, by this I mean the sequence of trees after composed, if they pack, then G, the sequence before composing packs. If I can show this, then remember the eventual iterate already packs. Then by induction it follows this guy, showing this is enough to show G packs. Instead of composing all functions, I can only choose to compose the largest tree. Even if you just compose the largest tree, that's not a star, you continue this iteration, it still becomes a sequence of star. Instead of composing the largest tree, I can only compose the furthest leaves from the largest tree. If I compose furthest leaves of the largest tree and continue iterating, this will also create a sequence of stars. So if I can prove in this sequence where I continue composing leaves of the largest tree, that's not a star, the tree after composition, if it packs, then the tree before composition packs, I would have proved the entire thing. Does that make sense? So this is using the idea that the eventual iterate packs, so that if you can, so now you just need to prove an implication. If this guy packs, then this guy packs. If you can show that, then that's enough. I'm sorry for bad drawings. But then what this is saying is, to recap, this conjecture is equivalent to this, the functional language that we created earlier, to showing a point, there exists a point where it's non-zero, to showing the remainder is non-zero, to showing this polynomial of the composed, this is the sequence of trees where the largest tree has been composed, but everything is the same. Not only the largest tree, the last leaves of largest tree has been composed. If this not zero implies this not zero, which is same as this is not zero. But then this is, turns out, is not too difficult, because after composition, all that changes is the edge labels of the largest tree that include these vertices from the leaf. This LG is leaf. So polynomial, remember, was checking that all vertices are different and all edges are different. I can factor them out such that this guy checks for the smaller trees, and this is for the largest tree. Even for the largest tree, the non-leaves do not change. Only the leaves are going to change, right? So PG tilde, by that I mean the polynomial of the tree after composing. Only this guy changes, because I didn't compose any of them. I only composed the leaves of the largest tree. But we know exactly how this changes. Instead of, remember the edge levels were y minus this guy and y minus this. Instead of g of v, for the last leaves, it becomes g squared of v, because that's the one that's composed. The edge levels changed by this. But then I can do a telescoping here, and I can bring in these variables, minus this and plus this. And turns out this guy I can rewrite as, by this telescoping, I get this guy back. And this is some remaining things. You see what I've done here is this guy changed, but then I've been able to, I got this square term, but by adding this guy and subtracting this guy, I'm able to get a thing that belongs to this guy again. So then what I can do is I can write the composed edge polynomial as uncomposed plus some extra stuff. So what I've done is the factor that changed, now I can write in terms of this guy plus some extra stuff. And notice that this times this is the polynomial of the pre-composed trees plus some remainder. And because what I've done is written this polynomial after composition in terms of polynomial before composition for plus some extra stuff, you can again take mod, the usual relation, and this bar basically means the remainder after you do the mod thing. The remainder of this is remainder of this plus remainder of this. Remember, we want to prove this thing in the top. What we actually want to prove is this not zero implies this not zero, right? We wanted to prove if the composed thing packs, then this thing packs. But then the contrapositive of that is this zero implies this. So this is the statement we want to prove. And we have this. So if the header was not true, if this was zero, but this was not zero, then this guy and this guy would have to be equal, and they would not have to be zero. So my job now is to prove there is no way this guy and this guy, which came out of my artifact of this introducing these extra telescoping variables, there's no way they can be equal. And that is exactly how we conclude. The argument is so there's one last thing where, so this, remember, is the polynomial of the graph after composition. And the polynomial is entirely defined by your function, the set of functions. So if I take two leaf variables, let me draw this. So let's say this was our largest tree G, and this was your leaf L, and L went to G of L, right? That's how these trees are, and this guy went somewhere, and this guy actually went to, I guess, G square of L. So how do I create G tilde? G tilde is created such that this leaf is composed. So what happens now is this leaf gets composed, and in G tilde, L and G of L both point to this guy. But then these and these now become leaves of the composed function. Because these are leaves, I can transpose them, and we show you can transpose this, and this is still in the automorphism of this. The polynomial does not change when you transpose these leaf variables. And this should be intuitive because the function itself does not change. The polynomial is created entirely out of these functions, and it lies in automorphism of that. But then because this is equal to this, that means that automorphism has to be in this guy. Remember, this guy is all this times this, all this times this. So it has to be an automorphism of this polynomial. But we know exactly what this transposition of these two variables does. It changes this guy. It doesn't matter what these really are, but it changes a factor of this guy so that it changes to this. And we know exactly what Q polynomial is. And turns out there is nothing that looks like this to account for the transposition that changed that polynomial. And V and this does not change because these do not contain those variables to begin with. So what has happened is we've converted this guy to this plus this. And if this guy vanishes, then this polynomial has to be equal to this times this. And what we've shown is that tau that has to lie in this guy cannot lie in this polynomial because it cannot keep the polynomial unchanged. And that is a contradiction. And that's the ending argument to how this works. If I go back to this, I think this is the main meat, is this transformation of these problems to another problem, so that I can show, I can convert this guy into this polynomial and show if it was not true that this was 0 and this was not 0. There should be two polynomials that are equal, and we show those polynomials cannot be the same. That is it for how this proof works. I just wanted to say the same method of converting trees to functions, and then creating a polynomial, showing this polynomial mod certain relation is not 0, converting the composed polynomial to pre-composed polynomial, and showing this contradiction. This general framework has been able to solve other problems, such as every tree on n edges decomposes this complete graph. And we've been able to strengthen that by changing the polynomial a little bit. Not only it decomposes k2n plus 1, but it decomposes these other graphs as well. And I guess to wrap up, what has happened is we have turned these trees to functions f. Not only functions, but functions then composed to these special functions that describe star. And in all these cases, stars always very nicely, very easily accomplish what we want to accomplish, like packing complete graphs. All these problems that are related to packing complete graphs, stars easily do that. And f to f star, this is done by composing. So this is composition. So what's happening essentially is the properties that are true for stars, and there are certain properties that are true for stars, and we want to know if they are true for all trees that are not stars. And everything becomes a star by composition. So essentially, if you undo this process of composition, it's saying there are certain properties that are invariant under this composition that's happening. And there could be other properties that stars easily satisfy, but because there is this family of things that behave very nicely under composition, there could be other properties that all other trees may satisfy. And there are other graphs that can be represented as functions, such as cycles. So it is cycles and trees and mix of those. So there could be properties that one might explore, because the way to represent these graphs as function allows you to use other tools such as polynomials, which is not commonly done in graph theory. I think I'll stop here and ask for any questions.
All right, let's take the speaker first. Thank you very much.